All right, if I get your attention up front, we are starting today with section 4F. Shh. So we've talked about discrete probability distributions. We learned how to find the mean and standard deviation, measure of center, measure of spreads. We can do it by hand and with our calculator. We talked about graphing discrete probability distributions using which type of graph? Histogram, gold star, very good. Turns out that the two distributions we are going to talk about this week, next week, behave the same way. We can graph them with a histogram. They have a mean and a standard deviation as their measure of center and measure of spread, but they are nice in that they are predictable and they have shortcut formulas for their center and spread calculations. And so we like these two distributions. The first and second that we're talking about are also very common, which is why they are on the AP test. We are going to focus today on binomial distributions. What does the prefix 2 mean, or binomial mean? I just gave you the answer, too. Oh, it is Friday. It feels like a Friday. So we call them binomial because there are two possible outcomes. So when we are checking whether a discrete random variable is binomial, the first thing we're checking is it binary? Two possible outcomes. We list them as success or failure, one or the other. That's not in a judgmental sense. It's just a success is an outcome I'm interested in. A failure is the outcome I'm not interested in. It's not like one is good and the other is bad. Just the success is the thing I'm keeping track of. The failure is the thing that's not interesting. The next thing we look for is that the trials are independent. With things like coin flipping, rolling dice, we know that individual rolls or flips are independent. If I'm doing things like drawing cards from a deck of cards, in order to be independent, I have to take those cards and put them back after I draw them. So I take a card out, write down what I got, put it back in and shuffle before I draw again. Next, the number of trials must be known ahead of time. In other words, we say the number of trials is fixed. If I'm doing some random process with coins, I need to know how many times I'm going to flip my coin before I start. Yeah? And the last is the same probability condition. Meaning that the probability of success is the same for every trial of the process. Each time I flip the coin, I have a 50% chance of flipping heads. Every time I roll a pair of dice, I have a 1 in 6 chance of rolling doubles. The probability of success is the same every time I do the thing. So if you know you're looking at a discrete random variable, the first thing you should check is bins. If it satisfies the conditions in bins, we know that it is binomial. Okay. We like acronyms. First we had socks, now we have bins. All right, so this is a binomial setting. If x is the number of successes in a binomial setting, we refer to it as a binomial random variable. We're going to do a little thought experiment. If I flip a coin 3 times, what is the minimum number of heads that I could possibly get? 0. I could get no heads. Or I could have 1 head, 2 heads, 3 heads. What's the maximum number of heads I could have out of 3 flips? 3. So this counting keeps going all the way up until I reach the number of trials that I'm doing. If I'm flipping the coin 3 times, it goes all the way up to 3. I'm flipping the coin 10 times, it's going to go all the way up to 10. And it always starts at 0. It is possible I get no successes out of those number of trials. So 0 all the way up to n. The distribution that results from looking at all those possible outcomes, 0 to n, and their probabilities, is called a binomial probability distribution. Because statisticians are very creative. And we're going to introduce some new notation. Beneath that little blurb, you see x, and then a little squiggle, and then a b with some parentheses behind it. So the first part of that expression where it says, why is my pen not cooperating? It says x and then the little squiggle. We read that as x follows. Any guess what the b stands for? What type of distribution are we looking at? Binomial. We're looking at a binomial. Those two blanks will always be the same two numbers. The two pieces of information I need about a binomial distribution are the number of trials n and the probability of success p. I will always give those two numbers with a binomial distribution. So we're going to do some practice. It says determine whether the given random variable is binomial. If it is, state its probability distribution. So example A says keep rolling a pair of fair 6-sided dice until doubles are rolled. Let x equal the number of rolls needed. Take about 90 seconds in your small groups and discuss. Is that a binomial random variable, yes or no? And why? How do you know? You should talk to each other. Articulate what it is you are thinking. Lost about what? 4 things you're checking, right? Bins. You're checking bins. So the first question is if you roll a 6-sided dice and you're looking for doubles, what are the 2 possible outcomes? Doesn't matter that I have 2 dice. What matters is that I roll the dice and I'm looking for doubles. What are the 2 possible outcomes? Forget the probability. What outcome do I want? You want it to have no. Oh, frowny face. Frowny face. Okay, let's go through this as a class. Before I pull up my random name generator, do I have a volunteer? I do not. Okay. Jaylene, did your table think that this was binomial or not binomial? But you were checking bins. Had you found in any of the things in bins that were not checked off? That was true. So if we go through bins, the B was true. You're either doubles or not doubles. Good. So we're rolling dice. Does the second roll care what happened with the first roll? No. So that one's checked off. For number of trials being fixed and known ahead of time, do I know how many times I have to roll until I get doubles? No, we found where the failure happens. I don't know how many trials I need, so no, this is not binomial. I could roll doubles on the first roll. I could not roll doubles until my 100th roll. I don't know how many trials I need, so it's not binomial. Also, binomial is keeping track of the number of successes. This is keeping track of the number of rolls I needed. That's very different than the number of successes. All right, next one. Chance at redemption here. Roll a pair of fair six-sided dice 100 times. Let W equal the number of times doubles are rolled. Give you another 60 seconds. Binomial or not, why or why not? And we'll try again. What are your two possible outcomes? I'm rolling my dice. What am I hoping happens when I roll my dice? Doubles. I'm looking for doubles. So all of my outcomes are either doubles or not doubles. Yeah, not doubles. So that's binary. We check the B. Go through the I, the N, the S. Vanessa, is example B binomial? Why is it binomial? So what are my two possible outcomes? I roll the dice. What do I want to happen? Doubles. So what's the complement to that? What's my other outcome? I got doubles or didn't get doubles. Yeah. That's binary. Doubles and not doubles. Perfect. Dice rolls are independent. Yeah. Fixed number of trials. How many trials are we doing? Perfect. 100 trials. We know that. Same probability. So on a single dice roll, each die has 6 outcomes. So that's 6 and 6. 6 times 6 is 36. There are 36 possible outcomes when I roll 2 dice. Of those 36 outcomes, how many of them are doubles? Could be 1 and 1, 2 and 2, 3 and 3, 4 and 4. I can't do 5 and 5. I'm holding something, right? So I get those diagonals, 6 diagonals. So yeah, so 6 out of 36 or 1, 6. And it's going to be the same every time I roll the dice because the dice don't care what happened on my last roll. Perfect. Yay. Good. On the FRQ, if you are asked a question like this, you should write this out. On the previous one, you would explicitly state where we put that X. I don't know how many trials I need to roll doubles, right? Explain where it fails if it fails. Good. Good. Questions on the front side? No. Take a deep breath before you turn that page. Nah. This is where we get all the grumbling. This is why everybody hates the probability unit. A polite reminder before we jump into this equation. Remember that for almost every ugly equation we see in our notes, the calculator is going to do it for us. So we know there are calculator commands coming, yes? We are looking at the formula so that we understand where the numbers are coming from and how the probability behaves. I am going to do an example of doing it by hand so that you've seen it. You are not going to have to do it by hand on your test. We are going to look at the moving pieces, though. So we're going to start with p to the x. What does that lowercase p represent? Probability of success. Probability of getting a success, and x is the number of successes. So this is the probability of getting x successes. Fighting with my TV today. The next chunk, q, and that should say to the n minus x. I made a little typo there. That should say n minus x. Q to the n minus x. Q, it is a q. Q is equal to 1 minus p. It is the complement of p. In other words, this is the probability of getting a failure. P is the probability of success. Q is the probability of failure. If x is the number of successes, n minus x is the number of failures. So what q to the n minus x is actually counting is the probability of getting that many failures. It looks really gross when we write it out with symbols. We have seen this before. This is just the multiplication rule. This is getting a heads and getting a heads and getting a heads and getting a tails and getting a tails. On our binomial activity on Wednesday, this is getting a correct and then a wrong, a wrong, a wrong, and a wrong. We know anytime we say and, we multiply. Yeah. The question is, what is that weird thing out in front doing? And if we still taught math like we should in the state of California, you would know what that is. It's called the binomial coefficient. You would see it in Algebra 2. You don't teach Algebra 2 anymore. Sad face. And what that binomial coefficient is doing is it is looking for the number of ways that I can get x successes out of n trials. And I am going to write that off to the side. Number of ways to get x successes out of n trials. While you are writing that down, I will give you an example from our activity on Wednesday. On Wednesday, you all took a quiz that was in Mandarin, and nobody in the room reads Mandarin, so we had to guess. And you were asked to fill out a probability table where you had to list all the possible outcomes. And we know that if we got one answer correct out of those 5 questions, there were 5 ways to do it. I got the first question correct, or I got the second question correct, or I got the third question correct, all the way down the chain. Yeah, 5 possible ways to do that. So 5(1) is the number of ways to get 1 success out of 5 trials. 1 question correct on a 5-question true-false quiz. That's what that is calculating for us. And there are 2 ways to find it. The first is a big scary fraction. The second is what's called a combination. Your calculator can do both. It can do that NCX command that exists on your calculator, but it turns out that exclamation point also exists on your calculator. Raise your hand if you have ever seen that exclamation point in a math statement before. That's about what I expected because that's what I saw in my morning classes. So let's take a look at what that is measuring. So this expression with a little exclamation point at the end is called a factorial. We are going to define them. The first two numbers I'm going to give you are definitions. The rest are patterns. So the definition, 0 factorial is 1, because that's what mathematicians said. That's just true. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. Can somebody tell me what 4 factorial would be? Yep. 4 times 3 times 2 times 1. For every number bigger than 1, a factorial is that integer times all of the positive integers less than it, all the way down to 1. So, all of this, I'm going to scooch you up a little bit. So, factorials and the NCX can be found in the same menu on your calculator. They are in the Math Prob menu on your calculator. You press the Math button, you go sideways to the Probability menu. I'm pretty sure that the exclamation point is option 4 and the NCX is option 3. Because we are doing probability calculations. Of course they'd be in the Prob menu. That makes sense. The reason that we're going over this is if you forget how to use your calculator or your calculator dies on test day, that is not what I meant to grab. On your equation sheet on the front side, they do give you the formula that I boxed in orange. That's on the equation sheet and it's labeled, but it's written just like I wrote it in that box. That's why I boxed that version of it. That's what they give you. So they're not going to give you the ugly fraction. You either need to remember that that binomial coefficient is the ugly fraction, or you need to remember that that binomial coefficient is just NCX, which is in your calculator. Yeah? So what we're going to do, because this looks like big scary math, is we're going to do 3 different variations. We're going to do one with the big scary fraction, and then we'll repeat it with the NCX, and then we'll do it with the command on our calculator. Yeah? I'm going to show you how to do all of these things. So if you don't already have your calculator out, please get it out now, because we are going to do an example. All right, while you're getting your calculators out, I'm going to read Pennsylvania Lottery runs a daily game called Treasure Hunt. Players must select 5 numbers, and they win a prize if at least 2 numbers match the numbers that are randomly selected by the Pennsylvania Lottery. The probability of winning a prize is 0.183. We are interested in the probability that a player wins a prize on exactly 2 of the next 7 days if they play the game once per day. we're asked to answer two questions. First, what we should do at the beginning of every question: define your variable, state its distribution, state any numbers of interest, and then determine the probability that a player wins exactly 2 of the next 7 days. So, the first question, 4A, what are we interested in keeping track of? I'm playing the lottery for 7 days. What am I keeping track of? I'm playing the lottery. What do I want to happen? I want to win. I'm keeping track of the number of days he wins when he plays. Yeah. So this is number of days we win. Happy face. Out of 7 days that we play. And then we need to state the distribution. And we know it's probably binomial because we're in the binomial distribution unit. We should still mentally go through the bins check. Binary, what are my 2 outcomes? Win, lose. Good, very good. Independent. If I won on the first day, does that have any connection to whether I win on the second? No. Number of trials. How many days am I going to play this lottery? 7. Very good. And then what is the probability of winning the lottery on any given day? 0.183, which presumably is the same every day. Good. We check bins. So we know X follows a binomial distribution. And in those parentheses, number of trials, probability of success. I defined what X was. I indicated which distribution it followed and gave the relevant values for that distribution. Now comes the math. Okay, so I want probability that X is exactly equal to 2. I think I'll do the combination one first because that's going to take up less space. So I know that that binomial coefficient n, X, is NCX. N is my number of trials. How many trials am I doing? 7. How many times do I want this player to win? Twice. So I'm looking for the number of ways to win 2 days out of 7 trials. Times. And then I'm going to do probability of success, 0.183, raised to the number of successes, which is 2. I'm going to square it. Times. And then I'm going to pull the number of, or not the number, the probability of failure. And I know success and failure are complements. So to get the failure probability, I subtract 1 and success. And somebody should check my math, but I'm pretty sure that's, yes, thank you. It's been a long day. And I want to raise it to the number of failures. If I win 2 days, how many days did I lose? Playing 7 days, so 5. Played 7 days, 1, 2, lost 5. On my calculator, I know to pull up that NCX, that 7C2, I'm going to go math, prob, and choose option 3. So math, prob, 3, it's going to give you spots to enter the 7 and the 2, right? And then the rest. So probability squared times probability to the 5th Can I get a thumbs up? I see nodding. I see some thumbs up. Yay. So the only trick with this was remembering that binomial n over x meant ncx. I know where NCX is on my calculator. That's not too bad, not too demanding, particularly when they give you this part of the equation on the equation sheet. And they label it binomial probability. Next, I'm going to show you what it looks like without the NCX. Because I mean, and I had to do this without a calculator when I took it. So the other way to do it is we remember the fraction. And I know that NCX is n factorial, so n is 7 trials. And then it's x factorial, x is 2, times n minus x factorial, which is the failures factorial. How many failures did I have? 5. The rest of this looks the same. I have a recommendation for you. Do not bother putting that in your calculator. You have to go back into Math Prob 3 times to pull up an exclamation point each time you need it. You don't have time on a test. It is faster to simplify this by hand. What does 7 factorial look like? Yep, 7 times every number less than 7. Good. On the bottom, 2 factorial. 2 times 1, 5 factorial. I see some stuff in that fraction that cancels. Yep, 5, 4, 3, 2, 1. Generally, the failures or the successes, whichever one's bigger, is going to cancel. What I am left with is 7 times 6 over 2. What is 7 times 6? 42. 42 divided by 2 is 21. This whole ugly fraction is just 21. And way faster than having to go back into Math Prob 3 times to pull up a freaking factorial. Right? We're lazy. And I bet if you run that in your calculator, you should also get 0.256 rounded. Yay. Now, for the lucky part, because you guys are born in the age of technology, there is a command that does all of that without having to use any ugly math. On your calculator, under the distribution menu, is a distribution called Binomial PDF. Stands for Binomial Probability Distribution. Where is the distribution menu on your calculator? Second, and then a button. Which button? VARS. Second VARS. Very good. You can see DISTR above the VARS button. So second VARS and Binomial PDF is option A. It's way down at the bottom. And if you press enter to open up option A, Binomial PDF, you should see it asks for 3 things. It asks for the number of trials. How many trials are we doing? 7, perfect. It asks for the probability of success, 0.183. It asks for the X value, which for us is what? 2. We want 2 successes. When you write it on your test, you need to include the labels. You cannot just write 7, 0.183, 2. Write the labels. Yes. And when you do that, what do you get as an answer? Yeah, which rounds up to 0.256. Exactly. Good. So my suggestion, given that up until today you've never seen a factorial, and you've probably never seen a combination, is use your calculator to do this. Just make sure you're writing out what the things you're plugging into the calculator are. Yeah. We're going to do another example. You get practice. Practice is good for you. Next example. Refer to the previous example, Pennsylvania lottery. If a player plays this game once daily for the next 7 days, find the probability the player will win fewer than 2 prizes. Fewer than 2 prizes. Fewer than 2 prizes, what math symbol goes in those parentheses? This is a less than 2. Yeah, less than, less than. Fewer than 2, 2 is not included. Out of all of my possible outcomes, only 2 of them are less than 2. Which numbers are less than 2? 0 and 1. So this is asking for p x equals 0 plus p x equals 1. On my calculator, I am going to pull up the binomial for 0. Second bars, binom PDF. I'm going to enter my data. It should remember, meaning you should still have 7 and 0.183 in calculator. And you're going to change the x to 0. And then you're going to go down to paste, and it's going to stick that on your screen. Do not hit enter. Press plus, and then go back to the vars menu and do binomial for value 1. I'll give you just a second, and then I need an answer. I happen to have an answer because I am speedy. Deshauna might have an answer. What does Deshauna have? Yeah. And Shauna has 0.624 rounded. And I see some nodding. Austin is nodding. Drew is nodding. Yay, very good. What that tells me about this lottery is that more often than not, I don't win, or I win 1 out of the 7 days. So winning is not a common outcome. Much easier with the calculator button, yeah? All right. So on your calculator, you may have noticed when you were pulling up Binom PDF, there was another command there. We have 2. What we just did, Binom PDF, NPX, only does the exactly cases. Exactly 0 wins, exactly 2 wins, exactly 5 wins. The other command, Binom CDF, asks for the same values, but the C in CDF stands for cumulative. CDF keeps a running total. As x increases, it just adds the probability onto the previous one, running total. So CDF is finding the probability that we are less than or equal to that boundary value. Meaning my calculator can handle 2 cases, exactly equal or less than or equal. If the problem I'm solving is not either one of those, I need to rewrite it as one of those. So we are going to practice doing that. So, do I have somebody who can read this example for us? Thank you, Drew.
A local fast food restaurant is running a draw free, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from the standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. On the first day of the promotion, 250 customers placed lunch orders.
Very good. Thank you, Drew. So, part A, find the probability fewer than 10 of the 25 customers won a free lunch. Before I touch that, define my random variable, determine its distribution. So, the first question is, what are we keeping track of? These people are going up to this computer. Yeah? Selecting a number. The computer is determining whether they get the free lunch or they have to pay. What are we keeping track of? Number of free lunches. Yeah. We know it's almost always going to be a number of something because we're talking about discrete distributions, and that's what discrete distributions do. They count a number of things. And then we go through the bins check really quick. So, what are my two possible outcomes? Free lunch or I have to pay. Good. Free or not free. Are those computer outputs independent? That's the assumption. Yes. Good. Number of trials. 250 customers are going to go up to this computer. Very good. Probability of success. And there's where we have to do a little bit of thinking. So we're using a simulated standard deck of cards. How many cards are in a standard playing card deck? 52. Of those 52 cards, how many are 3? 4. So we do have a fixed probability of 4 out of 52. So we do check bins. So X follows a probability distribution that is binomial. We are doing 250 trials. For each trial, there is a 4 in 52 chance of winning. 4 threes out of a deck of 52 cards. And because it's simulated, I'm not actually taking cards in and out. The assumption is it's pulling from 52 every time. Okay, now we're ready to tackle A. A says, find the probability that X is fewer than 10. Is my calculator able to do fewer than questions? No, it does equals and it does less than or equal. So I'm going to make a list of my possible outcomes and see if I can rewrite that. So the smallest number of free lunches is what? 0. Nobody could get free lunch. And it counts by 1 all the way up to 250. I don't need to go quite that high, but I am going to go up past 10. List of my possible outcomes. Fewer than 10. My cutoff is here between 9 and 10, and I'm looking at the guys that are less than 10. I'm looking at this chunk of my possible outcomes list. What is the biggest number in the section that I just boxed in blue? 9. So this is X is less than or equal to 9. Less than or equal to 9 is something my calculator knows how to do. I know that that's binom CDF or PDF? CDF, cumulative. My number of trials is 250. My probability of success is 4 out of 52. My X value is 9. The less than or equal to is the CDF, and then trials, probability, upper bound for my probability. And the question is, what does the calculator spit out? 3.6? Isn't it this?
3.6.
Is it 3.6?
Yeah. Oh, 0.0. Okay, never mind.
It's this, right? Yeah, that's okay, right? Yeah, I see some nodding. Thank you. It's like I've done this twice before. I'm pretty sure we should get the same answer in all 3 class periods. That's it. I need to look at your calculator because I'm getting 0.006128 something, and I see some nodding. Oh, there you go. There you go. So you got something smaller because you were looking at one data value instead of a range. Good. That's okay. We were able to figure it out. Good. Part B asks us a question about that answer. B says, in actuality, after these 200 customers has gone through this computer process, only 9 of them got a free lunch. Does this result give convincing evidence that the computer program is flawed? Explain your reasoning. So we know that the probability that 9 people or fewer got a free lunch is 0.006 or 0.6%. I want you to take about 90 seconds in your small group and discuss, is this an indication that that computer program is likely broken? Discuss. 90 seconds. I'm going to call on a random person. Make sure you talk to your neighbors. Thank you. All right, Nancy. What is your table thinking? Is this evidence that our computer program is broken? Cammie's nodding her head. Does Nancy agree with Cammie? Yes, so we suspect that yes, this is evidence that the computer program is broken. The question is why yes? Based on the fact that there is a less than 1% chance that 9 people or fewer get free lunch, I expect that the probability that exactly 9 people got free lunch should be less than that, right? The probability of getting exactly 9 free lunches is less than 1%, which means it is highly unlikely. Statistically speaking, I do not expect to see this outcome very often. So if I repeat this a couple more times with sample sizes of 250 and I keep getting low numbers, I'm going to send my code back to the programmer and say, hey, it's broken. It's not doing what it's supposed to do. You made a boo-boo when you programmed that synthetic deck of cards. Okay, so when I see you on Monday, we'll finish up binomial. We'll introduce our next one, geometric, and we'll spend the rest of next week practicing. Yay! Reminders, if I could borrow your attention for a second before we run for the hills. Homework 4F is posted. It is not due until the 17th, which is not next Monday, but the Monday after. The only things due this coming Monday, DE and your activity from Wednesday. Yeah? What's up? It's because I'm going on a good shape.